for the introduction and invitation. It's a pleasure to speak at this seminar. I understand that this ultra-broad cosmology is perhaps not the most usual subject of this seminar, so I'll try to give as much background as possible. Don't hesitate to interrupt me for questions or comments. So let me first recall this definition of wave cohomology theory. If we restrict to ultra-product cohomology to projective smooth varieties, that will give us wave cohomology theory. So we work with, let's say, a base field K. This is just a field of any characteristic. And we want a cohomology theory for projective smooth varieties with coefficients in the field of characteristic 0. The capital K is a field of characteristic 0. And the wave cohomology theory is a functor from the category of smooth projective varieties over small k to the category of graded K algebra over capital K. Well, this is technically a contravariant functor. And by grading, we mean grading that are non-negative. And we assume that hi of x for each degree has finite dimension. And of course, it satisfies a number of axioms. So, first one is Kunet's formula. It says that we have hx and hy is isomorphic to x y, and there's also pointwise duality. To give the proper statement for pointwise duality, we need this trace map, which is defined for any x in here. The trace of x is mapped from h star, well, actually, 2d of x twisted by d to k. This is the k-linear map, which is an isomorphism if x is geometrically reducible. So d denotes the dimension of x. And pointwise duality says that we have hi x times this 2d minus I x twisted by d by Kunet or by the multiplicative structure, this map to is 2d of x twisted by d, and by the trace map, this maps to k, and this defines a pairing between these two guys. And pointwise duality says that this is a perfect pairing. At least x is two-dimensional. So there's one last additional datum that is cycle-fast map. All right, class from the shell group, the shell ring to homology with even degree with appropriate twisting. And this is the ring homomorphism, which is contravariant in x, contrarial in x, and satisfying one axiom that if you compose this cycle-fast map for 0 cycles, it goes to a 2d of x twisted by d with the trace map, you get the usual the degree map, the degree of zero cycle Z, which can be embedded. So this is the commutative diagram. That's the only evidence here. And there are several classical wave cohomology theories. Let me start with the case of characteristic 0. This K has characteristic 0. Then we can take capital K to be K, and we have this Zheng cohomology theory. That's the wave cohomology theory. And also we can take if K is the subfield of C, we can take K to be Q, and we have the so-called Betty cohomology. This is defined using the analytic space, the contact analytic space is going to X. And we take cohomology with coefficient in Q. We can take, for example, singular cohomology here. And the two cohomology theories have comparison isomorphism, which are D. When you tensor that with C, with coefficient in Q, that is the same as H star of Zheng tensor with here's K. In particular, these two, if you restrict to each HI, they have the same dimension. So moreover, if you take so this H star B actually have an integral structure. This is isomorphic to H. The cohomology with integral coefficient B and where here, if you take each degree I, it is a Z module of finite type. It is a finite Z module. And there are other classical wave cohomology theories in characteristic 0. For example, there's also analytic cohomology, but they can be deduced from this Betty cohomology. Okay, but our focus in this talk will be on the case where a small k has positive characteristics. So now characteristic k is positive. Then in general, there are a lot of restrictions on the field of coefficient capital K. For example, there's the well-known classical counterexample of Serre, which says that if you take K, for example, to contain Fp squared, the finite field of P squared elements, then we can take supersingularized curve. Such that the endomorphism algebra tensor over Q is ramified at infinity. And B. And of course, this should act on our H2, H1, E. This will be a two-dimensional K vector space. And this implies that our K cannot be the field of rational numbers, or field of real numbers, or the field of p-adic numbers. So here in this case, the classical wave cohomology theories are the following two kinds. There's the tau analytic cohomology. So K can be a field, the field of analytic numbers, where L is a prime number different from B. And in this case, we have the analytic homology HR Lx defined to be H star of X, technically this is X, base change to K bar. And we take analytic homology, so homology with coefficients in the field of analytic numbers. In this definition, one way to define this, the classical way, is by a phase change from a homology with ZL coefficient. The ZL is the ring of analytic numbers. And this thing here is the ZL module, finite ZL module. It is defined as the inverse limit of a Zheng homology of Xk bar with coefficient in V over L to the NZ. The inverse limit is taken overall N. And okay, this is actually the definition. Okay, this is how we get one type of wave homology theory. Basically, this atomic homology is only well behaved for the torsion coefficient. So in order to get from torsion coefficient to coefficient in character 0, what we have done here is to take the inverse limit, and then we take the field of fraction. There is another classical wave homology theory in positive characteristics, namely the Christian homology. So in this case, K is the vacuum field of the ring of bit vectors of K. And we can take Christian homology of X over W and enter with K. Okay, but in this case, the isomorphism. Sorry. In this case, the relation between different homology theories is more mysterious. So in the sense, first of all, there are more classical homology theories that are not directly related by comparison isomorphism. So here this L ranges over infinitely many prime numbers. So there are infinitely many wave homology theories. But we do know that they all have the same dimension, the same Betti number. So here's what we know, that the dimension. So from now on, we will concentrate on the analytic homology. This dimension of H star L X as the QL vector space, which means let's say 6 homological degree I. This is an integer independent of I. Sorry, independent of L. And this is a consequence of the base indexers that I will elaborate very soon. But another fact is that we also have some sort of integral structure here. So we can interpret this independence of L as saying that there exists a vector space, a Q vector space. So i.e. there is a Q vector space of finite dimension, V, such that each homology group is isomorphic to V tensor with QL. Of course, this isomorphism is highly non-canonical, but there exists for each I and X such a Q vector space and an isomorphism like this.
So, excuse me, first of all, for this X is smooth projection? Or?
Yes, this X is smooth projection.
So if you do not assume smoothness, does this still hold? Or?
Yeah, that will be the subject of the
okay.
talk, actually.
Okay.
That's a very good question.
Yeah.
So here I assume that axis is projected. Okay, but even in this case, we can ask another question that is about the integral structure here on B. And it turns out that there exists a finite V module M such that HIL back is isomorphic to M tensor with QL for all L. Different properties. So this is a theorem of Gabor. And if you think about it, it simply says that the first statement is true, plus the torsion freeness of analytic homology. So of course, this is to be interpreted as homology. Yeah, what I meant is this. Coefficient in DL, so the shy of, I mean, rewrite here. So of course, here we have to, we're talking about integral structure. So there exists a Z module M such that the integral analytic homology of X is isomorphic to M tensor with DL for OL. This means two things. First of all, that the rank of each of these DL modules is independent of L. And secondly, that they are torsion free for L large enough. This HI, the coefficient DL is torsion free. So basically, the torsion is bounded by the Z module. And this proof of theorem of Gabor also uses the Weis conjecture, but it also uses a stronger form, a fine result in Devin's proof of the Weis conjecture in the DCD theorem.
Can you modify your camera so it can cover the whole board, because there's a little bit missing on the right of the board.
On the right of the board, okay.
Yeah.
So I can see all of them, but sorry. Is this better?
Yeah, it's better. Thanks.
Okay, so now I've explained this implication of the first statement that Weis conjecture implies the independence of L of this dimension. The Weis conjecture is a conjecture about data functions of smooth projected varieties over a finite field. So here, K will be the finite field. And the data function of a variety is defined by counting the number of rational points and the number of points with values in the finite extension of the base field K. We count this number, we divide by n, multiply by t to the n, and we form this series and we take the exponential. And by definition, this is a formal power series in with values in with coefficients in Q. So the Weis conjecture says, first of all, that this is a rational function, which follows from the homological interpretation. So this data function is also the product of determinant of 1 minus the covariance acting on the homology at the H star L. I plus 1 power. So this is actually a rational function. And the most difficult part of the Wave conjecture, the theorem due to the mean, is that this the Frobenius action should be on the analytic homology of HI of X are by so the eigenvalues of this action, alpha is the eigenvalue, then alpha is a so-called Q-way number of weight I, which means that for any embedding of Q of alpha into T iota, the absolute value of iota alpha is to be higher. This implies in particular that alpha is algebraic over Q. So as a consequence of this, the Wave conjectures, we see that all these polynomials, these characteristic polynomials here, can be read off from the data function. In particular, the determinant here, the polynomial, actually is a polynomial with integral coefficient, and it is independent of L. And in particular, the dimension of this space is independent of L. Okay, so you see that this the first part of this fact follows from the Wave conjectures. And now there are deeper problems about L independence. Already in the definition of the Wave homology, we mentioned this cycle path map from X to so we say that the cycle is more generally you can do this for any Wave homology theory. And we say that two cycles are homologically equivalent if they have the same cycle path in the Wave homology. And a very important conjecture in Grothendieck's conjectural theory for a universal homology theory is the homological standard conjecture, which says that this homological equivalence is actually the same as the numerical equivalence. And in particular, if this holds for all Wave homology theories, then all the homological equivalences are the same. So in particular, we have this equivalence for the analytic homological equivalence is independent of L. So here X is still assumed to be projective smooth. But it turns out that this deep conjecture, so this independence of L of analytic homological equivalence, can be expressed more elementarily, at least in the case where K is the algebraic closure of a finite field. If K is Ft bar, then this independence, the remark, is independent of L is equivalent to the question raised by Gaohua. So this is equivalent to condition that for every X here, X is no longer assumed to be projective smooth, which is separated of finite type over K. We can still talk about the analytic homology be more precise here. So we want to use here the compactly supported cohomology with value in QL. This is a finite dimensional QL vector space, and we ask that the dimension is independent of L. So this equivalent to the theorem of von Zheng. Ready? And it's still widely open. So today I want to discuss the refinement of this independence of L. In view of the interpretation of zeta function, this chronological interpretation of zeta function, and how it implies independence of L of Belly numbers in the projected smooth case, we can ask whether when X is defined over a finite field, the Frobenius action, or at least the characteristic polynomial of the Frobenius action on this cohomology is independent of L. We can ask the following questions, which refine this conjecture here. So A, do we have, so in the case where X is, here, the X is separated and a finite type over a finite field. Do we have that the Frobenius action on the compactly supported analytic cohomology is have characteristic polynomial belonging to Z of T, Z bracket T, that's independent of L. And we can also ask whether this Schaber's theorem holds in this case, namely whether this cohomology with a DL coefficient is portion free for L starting now. And in fact, we do know the answer in a few very sessions. So we can ask these questions A, B, not only for this compactly supported cohomology, we can also ask the same questions for the zero cohomology or the intersection cohomology. And so on. So let me say the positive result. So the theorem. So first, for the case where X is proper over K, then A and B hold. Maybe that's three-dimensional. Then A and B hold for the intersection cohomology. Okay. The second, if X is assumed to be smooth and equipped with a morphism F, which is proper over a curve, in this case, and B holds for the Euro cohomology and the compactly supported cohomology. And moreover, it also holds for homology of the fibers of S. So then we have star of S, where S is a growth point of C. That's bar. So in particular, this gives examples where the questions hold for X. X is smooth but not necessarily proper. And for the fibers X and bar, they are proper but not necessarily smooth. So we have results for both these cases. And actually, Van Dam and Bruin also proved that this equivalence, this L independence for homological equivalence holds as long as the second assertion is independent of Betty number holds for smooth variety. So without going to the general case of finite type separated speed. Okay, any questions so far? So this theorem right down what? In the case where X is proper and equidimensional for the intersection homology, part 1a is the theorem of Gaber. And part 1b and part 2 the joint work with Anakadale. In the rest of the talk, I'll explain our strategy of the proof.
So for the second part, so this implies if you take a smooth proper variety, then this holds.
Smooth proper variety,
then A and B holds. I mean, you can just take the product, or in the second statement, do you assume F is not trivial?
You mean take X to be a smooth proper?
Yeah.
Yeah, but that case was already known. It was the theorem of Zheng.
Yeah. So you give a new proof, or?
No, but here our X is not proper. So this curve is not a complete curve.
Okay.
So this is more general, so we don't assume it to be proper.
Okay. I mean, for their cases, so you give a new proof for their theorem. Or you use that, you need their theorem.
The theorem of Gaber or the theorem of the theorem of Gaber is for projected smooth.
Yeah.
And it was extended to proper smooth by Saul. And our case, so we don't assume properness in this statement. And actually, we do give a new our method is different from that of Saul.
Okay, good.
So our method is uses this ultra product homology in the title. That's what I will explain next.
And in this theorem, is it important that K is a finite field? In the theorem, is it important that K is a finite field, or does it hold more generally?
Because as stated, the theorem for so here is about the determinant of the characteristic polynomial of Frobenius. So for A we need finite field, but for B, just by spreading out, it doesn't really matter.
Okay, thanks.
Okay, thank you. So now the second part of the talk is about autocratic. So the idea is really simple. So previously we worked with analytic homology, and it was defined using inverse limit. So the ring of analytic members is defined to be this inverse limit. And then to get a field of, so this ring is the DVR, and it has a generic point. It has a minimal ideal, and this minimal ideal has residue field QL, which is of characteristic 0. So to go from characteristic positive characteristic to characteristic 0, we took this inverse limit, and then we look at a point of characteristic 0. So there is the much easier way of getting to characteristic 0. We can simply take the product of all the Z over L for varying L. So let me call this R. So let me pick some notation. Let me write script L to be all the prime numbers different from me. And for all the L, we take this finite field Z over L, and we take the product. So this R is a ring of Crow dimension 0. It is not Noetherian. We can actually embed L into spec R by sending this number L to the ideal generated by L, which corresponds to the projection of R onto the vector indexed by L. And those points will be of finite characteristic, but all the other points are actually of characteristic 0. So you can choose any point that is in the complement of this embedding. So choose any M in spec R minus L, and then it will be it's a maximal ideal. So you can either take the localization or you take the residue field. It's the same thing, and you get a field of characteristic 0. And this is our ultra product. So this is a very classical construction. So this is as a topological space, spec R is the stone check complexification of L. And there's a description in terms of ultra filter, which I'm going to. So by a filter on L, we mean a subset of the power set of L, such that there are two axioms. First of all, if A belongs to F and B belongs to F, then A intersects B belongs to F. And if A belongs to F and A is contained in B, contained in L, then B belongs to F. And we say that a filter is an ultra filter if it is maximal among the proper filters. And for each ultra filter, you can easily associate a maximal ideal of R by there's a bijection here. Then this ultra filter Q with this maximal ideal MU, which is defined to be all the elements AL, such that those L with AL equals 0 belongs to U. Okay, and you check that this is a bijection. And the image of L in this set, so the subset of ultra filters corresponding to the image of this embedding is called the principal ultra filters. So basically, the principal ultra filters are of the form UL, which are those which consist of those A that contains a certain L. Those are called principal. So they correspond to points of stack R of positive characteristic. And if you remove this point, all the other points, let me give a name. So U is the set of non-principal ultra filters. So every element of U will correspond to a maximal ideal of stack R, whose residue field is a field of characteristic 0. And this field is called the ultra. This field is called the ultra product, and we denote it by QU instead of QL. So there's another description of this QU. We can more directly view it as the product of all the FL, L in L, divided by this equivalence relation to the U, where two set of elements are equivalent with respect to U, which is defined to be, you look at those indices for which AL equals BL, and you ask that this set belongs to U. And the advantage of this description is that it really applies to any algebraic structure. It doesn't have to be a field. This applies to sets, to vector spaces, or even to categories. So when we give a notation, we write this as the product over U of all the FL, which means this quotient here. So there's some curious fact about this field. This is a field of character 0. There's an extension of Q. But it inherits a lot from finite fields. In particular, this is called the pseudo finite field, which means here that this GABA group of QU is actually the head. It's the topological cyclic group. Moreover, it satisfies the Hilbert-Nusselt method. By which I mean every geometrically reducible QU variety has a rational point. So there are many ways to think about this QU, but it ultimately doesn't really matter here. If you like, you can also replace this QU by QU bar. It doesn't. Both are the questions A and B we raised are not sensitive to taking a field, a finite algebraic extension of the coefficient field.
So in the Nullstandssatz, do you mean positive dimensional irreducible variety? Because if it's just a spec or finite extension, then surely it does not hold, right?
But I mean geometrically irreducible.
Oh, sorry, geometrically irreducible. Yeah, thanks.
Okay. Here, so there's a name for this. I think field satisfying this property is called a PAC field, for pseudo-algebraically closed. This is also called a PAC property. Okay. Anyway, now that we have this field, we can define a cohomology in this field with basically the same method. So we just take ultra product. This is called the ultra product. By first taking the product and then mod out by this kind of equivalence relation defined by this ultra filter. So one can define a cohomology HI xk bar with coefficient in QU. This is defined to be this ultra product of HI xk bar of FL. So we can do this directly from a tau cohomology with a torsion coefficient. By taking the ultra product, we get something in characteristic 0. But there is something non-trivial here. So in order to show that this is a finite dimensional QU vector space, we are actually using the fact that the dimension of these cohomology spaces have bounded dimension. So we are using this boundedness of Benny numbers, which is true, but it's a non-trivial fact. Here's the definition of this is ultra product cohomology. So once this fact being established, it's very easy to check that the cohomology theory that's defined. If you restrict to X projective and smooth, it gives the Wei cohomology theory. So this is fact that was first observed by model theorist Tomaszek, that H star xk bar to U for X projective smooth gives the Wei cohomology. And this is a very large family of Wei cohomology theories, because for each ultra filter, U in U, we get this Wei cohomology theory. And there's this fact from set theory that if you look at all the non-principal ultra filters U, the cardinality of this is actually 2 to the C, where C is a continuum. So this is really, really huge. So we get a lot of new Wei cohomology theories. And we can now extend our question. So our question A becomes question A plus. So instead of asking this cohomology, so now K is a finite field and X is the finite type scheme separated over K, we can ask whether this cohomology, let me finish writing, meaning, we can ask whether this characteristic polynomial is independent of L. Here I have written Q dagger. This is the notation of Anna, which means that the dagger is either a prime number L or a non-principal ultra filter on L. So we can ask, this is independent of dagger. So we can expand our original question into the question of independence of dagger. So what we have gained here is because this definition, it is easy to see that actually this implies not only the independence of L, but it also implies torsion freeness for L large enough. So this actually implies both A and B. So we no longer need to study torsion freeness for analytic homology. What we have to do is to just study this cohomology, new cohomology series, this ultra-product cohomology in character to 0. Okay. So one thing that one gets for free once we get this wave cohomology theory is that this ultra-product cohomology also satisfies that form of wave conjecture that I stated. This is the theorem of Kaplan-Messing. But for the purpose of extending these results to those fibrations or those cases in the theorem that I stated, we need to establish more generally the decomposition theorem. So let me finish with a statement of the decomposition theorem. So the easiest, the simplest case of the decomposition theorem is when we have everything is so everything is projected smooth. Y is projected smooth. This F here is projected smooth. So X is projected smooth, proper smooth. So over, let's say, the segment Q. Or maybe segment Q bar. So we want to look at the array spectral sequence E to PQ, HP of XK bar, K is FQ. Our Q S lower star of QL. This converges to HP plus Q of Y. The cohomology effect. And it follows from the theory of weight that the right spectral sequence degenerates as E2. The decomposition theorem is a refinement of this degeneration. It tells us, so in this case, is there a question? Okay, in this case, the degeneration is the consequence of Deline's decomposition theorem, which says that this guy, this RF lower star QL, actually decomposes into a sum of R QF lower star QL shifted by magnitude. So this is the statement of the decomposition theorem in this case. Due to the mean. Now in practice, so the general decomposition theorem is the theorem when we drop the smoothness of F, and then you realize that this F lower star QL, so this kind of decomposition no longer holds for the usual T structure. So if you just take the usual cohomology sheaf, then this will no longer hold. But it holds with suitable modifications. The general statement of the decomposition theorem of DDDG is as follows. So So it is a theorem that was very generally for x, y proper, and we are no longer assuming any smoothness here. And in this case, it is also a decomposition theorem for coefficients, so we can take any coefficient L in the derived category of x that is perverse and pure. And then the decomposition theorem says that in this case, Rx over star of L has a decomposition similar to the above, but with this Ri replaced by Pri, which is the perverse truncation of Rx over star. And moreover, if this is the decomposition, second thing is called the hard-test theorem. So assume that f is projective. There exists f ample line mono L. And then by taking its first train class, eta, so by cutting with the I power of eta, we get an isomorphism from PR negative I of F lower star L to PR I F lower star L with a twist by L. So this is an isomorphism. So our main result is that we can do the same for ultraviolet homology. So this is not a rigorous statement, because I haven't told you what is the direct category of ultraviolet sheath, and most of the difficulty actually lies there. So we have to define a suitable category of ultraviolet sheath. And you can imagine if you just take any family of Eckelt coefficient sheath, and then you take the cohomology and take the ultraviolet, there's no way that that is a finite dimensional QU vector space, because you have to control, you have to bound the dimension of those cohomology groups. So basically, you need to control you need a family that is uniformly constructible, but that is not enough because there are phenomena of wild ramification. So you also need to bound the ramification. So one of the main ingredients of our theorem is that of a theorem of Orgogozo published in 2019 about the uniform constructibility. And I should say that so after this definition of the direct category, there's also this hard work about weight theory, and most of that was built by Anna. Okay, let me stop here.
Okay, thank you very much. Thank you for very nice, very interesting talk, actually. So we have some few minutes for questions or comments.
So you were discussing these ultra products and they were indexed by natural numbers. You just take product of finite fields FL for all different L over some ultra filter on N on principle. What happens if you take larger sets and ultra filters on them? I mean, do you get something new or just like imagine you have
by larger. I already take all of
for
them.
instance.
Yes.
No, but your set could be larger. Like you could have a set whose cardinality is, for instance, a continuum, or I mean, cardinality of real numbers rather than natural numbers. And for each element of that set, you have a finite field some FL where L is different from P. And then you take an ultra filter on that large set, like a set of real numbers, and then you take an ultra product over like that. So that would give you a larger class of fields QU to play with, and I'm just wondering whether you get something genuinely new by doing that, or
that's a very good question. We haven't thought about that. Yeah, what we try to do is to do the minimum. So we have taken the least possible. We just take an infinite set, a countable set of finite fields, then we take the product. But when you take ultra product with of a larger family, then you get a field whose cardinality is no longer bounded by the continuum, and the usual way of...
Well, the cardinality will be bounded. The cardinality will be bounded by the cardinality of the set that I mean, it will be a function of the cardinality of the set on which the ultra filter is.
No, I think
maybe
if it's a continuum, then the cardinality will be true to the C.
Yeah.
So I'm not
I mean,
sure.
that's
So usually we define this way by choosing an embedding. So the QU can be embedded into C. And I haven't thought about
those bigger fields will. Well, I don't know. It's I mean, I'm just wondering if you get something new. I think also for these larger ultra products, actually there are some new phenomena. For instance, it could happen that your ultra filter is countably complete rather than just finite intersection complete. I mean, and then somehow not all ultra filters are the same in that for those bigger sets. So, well, anyway, it's just a remark.
Yeah, thanks. Think about it.
Okay. Any other comments?
So in your main theorem, you stated for family over curve.
Yeah.
So why do you need the base to be a curve?
Yeah, basically, we just so this intersection cohomology is defined using intermediate extension, and we cannot actually control the behavior in each cohomological degree over in higher dimension.
Okay.
So what we know about L dependence is that it is this independence holds when we pass to the Grothendieck group. But in the case of let's say a surface, this intermediate extension will have several cohomological degrees, and we don't know how to separate them.
Okay. Thank you.
Okay, so the time is out, and let's thank the speaker.
Thank you.
And we shall resume in 10 minutes. Okay, at quarter past. Yeah, I don't know past what. It depends. Okay, but we'll have a short break for